I've kind of always been interested in computers. Ever since I was probably about 2 years old, my dad used to take me to work and I would like play on the mainframe and just type my name over and over again on it, which I was endlessly fascinated by. This idea that you could tell this machine what to do and it would do it exactly. So, learning BASIC and writing for loops and seeing that it would actually count to 1,000 when you told it to. I realized that data management was kind of one of the key problems with computers, right? We think of computers as something that do computation, but really 90% of what we use them for is information retrieval. Database is a very cool way to kind of think about how to make it easier for people who aren't experts with computers to still perform very complicated data management tasks. My work focuses on scale independence, which is an extension of data independence that allows you to maintain the productivity of relational databases and high-level declarative languages like SQL, while also getting the performance predictability of NoSQL key-value stores. My name is Michael Armbrust, and I'm a researcher at Databricks, and I'm a member of the ACM. So my name is Michael Armbrust, and I just finished my PhD here at UC Berkeley. I was working on this concept called scale independence, which we'll be talking more about, and I'm about to join this new startup called Databricks. So it all started back in the RAD lab, which stands for the Reliable Adaptive Distributed Systems Lab. And this lab was a 5-year mission whose moonshot vision statement was to allow a single person to design, build, deploy, and operate the next generation internet service, so with millions of users. And not only did we want to allow a single person to do this, but we wanted to allow them to do it in the course of a weekend. Kind of the thing that we realized here was that these modern web frameworks, think Ruby on Rails or Django, allow a single person to build a very compelling application very rapidly and put it out on the internet for everybody to use. But the problem is that once it becomes popular, you often end up with this success disaster, where the onslaught of users causes the site to tip over, and then you kind of lose your user base, just as you were starting to become popular. And so the goal here was to kind of use machine learning and systems to kind of solve this problem so that the computers could handle the scaling for you. So when we started this was right around the advent of cloud computing, which was awesome because it solved a lot of the problems. You no longer need to worry about buying machines and racking them and hooking them up in order to scale your website. Kind of just give Amazon your credit card and they take care of this. It turns out scaling up the application tier is also fairly easy. Once a web server starts getting overloaded, you just throw in another web server and split the load across them, and that works fine. But what we realized was a key problem was in the data tier. What do you do with the database? So a common pattern is for these web developers to start with something like MySQL or Postgres, and you build your application on top of that. But the problem is you can't just add more Postgres servers because you want to be able to run queries over all of the data that's stored on all of them. So one thing you can do is you can start to partition your application manually. So you kind of have to have multiple database servers. The application has to know which database server to talk to for what piece of data. And this is a lot of work for application programmers. So there was this whole rebellion against kind of traditional relational databases, and this new type of software, this new storage system came out called NoSQL stores. And so kind of the most popular example of this is just a distributed key value store. And so a key value store lets you look up data by key, so you can basically put and get by key, and that's the only operation that it supports. But the nice thing is that it trivially scales to hundreds of machines. So if things start running slowly, you just throw more machines at it and it gets faster. So examples of systems like this are Cassandra or MongoDB. And so kind of the nice thing here is now developers can scale their application easily, but writing applications against key value stores is very difficult, right? So SQL is a very powerful language. It takes care of a lot of the deciding how to execute a query for you efficiently, automatically. So the nice thing about declarative languages like SQL are you tell the database what data you want to retrieve, and it figures out how to retrieve it for you. So this is called query optimization. It is also known as data independence. So an application is independent of its data if you can change the layout of the data, add an index, remove a column, add a column, and the application itself doesn't have to change at all. So with a key value store, you lose a lot of these benefits. And so our question was, can we give developers the productivity benefits of a relational database while maintaining the performance predictability of these distributed key value stores? Scale independence is a new type of data independence where the database gives you a high-level declarative language where it can guarantee the worst-case performance independent of the scale or the size of the data that's being stored in the database. So if a query runs fast on your laptop with 10 users, it will also run fast when running on hundreds of machines with millions of users. And the way we do this is by putting a static upper bound on the worst-case number of operations that will be performed by any query, independent of the amount of data in the database. Yeah, so it turns out coming up with this upper bound is easy for some queries. So if you look at something like a query that looks up a user by their username. So username is often the primary key, meaning there can only be one person with that username in the database. So I know that when I do a lookup by username, I'm going to do one lookup, it's going to return one record, and it will be quick. So, in that case, it's kind of trivial to do the scale-independent analysis. But, of course, you can't write applications using only these very simple queries. You also want to do joins and kind of pagination and these other things. So what we found was we actually had to extend the SQL language. So we came up with our own version of SQL called Pickle, which stands for the Performance Insightful Query Language. And so it's SQL-like, but with some extensions. So one extension that we added is the ability to express cardinality constraints as part of the schema of your application. So it's very common for there to be limitations on relationships in modern web applications. So for example, on Facebook, you're only allowed to have 5,000 friends. This is reasonable because any person probably only can talk to so many people in their lifetime. But by giving this information to the database as part of the schema of your application, it can actually look at your queries and decide when it's safe to do a join, when that join is not going to blow up the size of the result set and therefore, hurt the performance of the application. And so what Pickle will do is if you try to write a query where you're running an unsafe join, it'll make suggestions to you about cardinality constraints that could possibly make the queries in your application scalable. And you can decide if they're semantically acceptable given the properties of your application. So that's one example of something you need to do, but it turns out that's kind of insufficient. Another problem is you want to be able to run queries that return arbitrary amounts of data. So, show me all of the tweets that Lady Gaga has ever made. I don't want to limit you to only 10 of them because you kind of want to go back and see all of the things she's been saying. But you also don't want this page to take an arbitrary amount of time to load and get worse and worse as she tweets more. So the typical trick here is you paginate it. So you return the results one page at a time. And that's great, but you actually have to be pretty careful with the implementation here, otherwise you can end up with performance problems. So if the way you run it is you start at the beginning and you skip all of the results you've already seen. So, first skip the first 10, then skip the first 20, then skip the first 30. You're going to end up doing n-squared work in order to return the nth page of results. And that's going to become unscalable eventually. And so we actually make pagination a native part of the language. You say, here's my query. I want this to be paginated 10 results at a time. And what you get back is kind of what's called a client-side cursor, which remembers where you were and allows you to pick up in the query where you left off without having to skip all of the results you've already seen. And by doing this, we can take this unbounded query and turn it into an unbounded set of queries that themselves are bounded. So each query that you run, each page that you load, will be guaranteed to have a worst case response time. Those techniques alone are insufficient. So that's kind of all of the queries that you can run on demand, where you're computing the answer as you need it. There's a whole class of queries where this technique is insufficient. But fortunately, what you can do is you can actually answer this query in a scale-independent way by pre-computing the answer. So what you're doing is you're fundamentally changing the scaling behavior of the query by shifting some of the work from query execution time to data insertion time. So an example here would be I want to run a query that shows how many people are following Oprah on Twitter. So that number is very large. You don't want to have to scan all of those tuples every single time to come up with the count. But if instead every time somebody starts following her, you increment the count by 1, and every time someone stops following her, you decrement the count by 1. When somebody asks the question, you just look at that answer there. Now that query is scalable. But pre-computation actually opens up a bunch of new problems. You now need to worry about the amount of space required to store the answer, and you need to worry about the amount of computation that will be done each time you insert a new data item. to figure out the space, it turns out you can actually analyze the functional dependencies. So we have this static analysis algorithm that looks at the properties of your schema and the properties of your queries and decides whether or not it's possible for the amount of space required to store this answer to grow kind of exponentially, which is what you want to avoid. So functional dependencies are these things that limit the types of data that can be stored in your database. For example, there's a functional dependency between social security number and name. Given a social security number, there can only be one name in the database associated with it. Another example is the cardinality constraints we were talking about earlier. On Facebook, if I know the user ID, I know there can only be 5,000 friends at most associated with that user ID. By looking at all of the functional dependencies that are present in the schema and in a query, you can actually figure out which queries are guaranteed to be only a constant factor larger than the data that's stored in the database. And so as a result, you can decide which ones are safe to pre-compute and store the answer to. And then for incremental precomputation, so this is when a new data item is inserted, how do I update all of my pre-computed answers? It turns out you can actually look at the incremental precomputation that you want to do as kind of a derivative of the query itself. So it's a query that you run when a data item is inserted, and it tells you what needs to be changed about the pre-computed answer. It's called a delta query. And so by looking at the delta queries, we can actually reuse our techniques that we used earlier on the queries before and see the number of operations that will be required in the worst case to execute that delta query. And if it's bounded, then you know the incremental precomputation is also safe. This idea of bounding things is great, but we wanted to show that you could actually maintain constant response time as you scale to hundreds of machines and run this for real. So we built this real system called Pickle. We tested it out with real developers because it turns out it's easy to build scalable queries if you've been thinking about it for years. But we wanted your average developer to be able to do this. So we took a bunch of Berkeley undergrads, we gave them Ruby on Rails and the Pickle system, and we let them actually build applications. Some of them just over the course of a weekend. They came up with some pretty cool ideas. They built this system called Gradit, which is a GRE studying tool, and they also built this resume management system for a company, which is something that was actually suggested by some of our corporate sponsors. And they built this in a weekend. We ran it on EC2. We scaled it up to hundreds of machines. In order to kind of simulate a website becoming very popular, we used this other project called Rain, which actually made requests, basically fake requests simulating real users against the actual web servers. And what we were able to show is that, over the course of a couple of hours, we went from 10 machines to 300 machines, and the response time, even in the 99th percentile, stayed constant. Testing on EC2 is great because it takes care of a lot of the machine management and setup for you, but still you need to find some way to get your application out there running on hundreds of machines. When something goes wrong, you need to bring back in the failures. If something crashes, you need to know about it. When things go bad, you want to be able to kind of scrap everything and start up the experiment again. So we actually built this library called DeployLib, which is available on GitHub. And DeployLib is this basically domain-specific language for managing hundreds of machines in parallel. It's written in Scala, and basically from the Scala REPL, which you can think of like an interpreter, you can actually issue commands that basically, you can deploy jars, you can run programs, you can retrieve log files, you can even just execute shell commands, and it runs them all in parallel on these hundreds of machines and returns the result to you as Scala data structures, which you can then inspect. So I can say, which of my machines has Java crashed on, and you can just write that and get the result back. Or, take this thing that I just wrote and deploy it on hundreds of machines. And one of the cool things is it actually integrates with the build system. So you kind of link this in with your application, and then it takes care of packaging up all of the dependencies for your application and shipping them to the cloud, distributing them to all of the machines, and starting it up. So when you find a bug, you can very quickly fix the problem and redeploy in a matter of minutes, which really, decreasing that iteration time, I think, is kind of key to being able to do effective research in the cloud on hundreds of machines. The key lesson from scale independence is that you don't need to abandon the productivity benefits of the relational database in order to build a system that scales. Simply by rethinking the way we do query optimization, we can preserve a lot of the benefits of the relational model while still getting the predictable performance that key value stores give you. If you look at a traditional relational database, kind of usually the way it decides how to execute a query is by trying to minimize the average cost. And that's great when you're just trying to make things as fast as possible. But when you're building these applications, what you really want to do is you want to minimize the chance that there's going to be bad performance for any of your users. So Pickle looks at the worst case performance. It comes up with a static upper bound on the total number of operations that will be performed. And that really gives you this predictability without sacrificing SQL. There are more ways for it to be expanded. So we did a pretty good job of expanding the space of queries where you can do this analysis and come up with this static upper bound. But I think there's more. And I think kind of a key direction to extend this is looking at how we can leverage parallelism to allow you to run even more complex queries kind of by throwing more machines at the problem. So in Pickle, we were able to maintain a constant cost per user by coming up with a constant upper bound on the worst case number of operations that will be performed. If instead you're willing to allow a query to use more computing resources as the data grows, what you can do is you can actually, instead of bounding the total amount of work, you bound the amount of serial work that needs to be done by a single partition. So now, as the data gets larger, you're just adding more machines, more partitions to it. But the amount of work that needs to be done by any one machine stays constant, which is going to allow you to kind of preserve the predictability of the application. This, however, opens up a whole new set of problems. Specifically, how do I evenly divide the work? So kind of a common problem when you're running things in parallel is data skew. One machine ends up with too much data, and so it becomes a straggler, runs slower than everybody else, and you have to wait for every machine to return before you return the result to the user. So in order to make something parallel scale independent, you actually need to be very careful about managing skew. And I think there's a lot of interesting research questions there about what sorts of relational operations are skew tolerant. One of the things that I'm kind of working on now is really building a framework for allowing you to do optimization research. So a lot of the work on Pickle was kind of rethinking the way that we build query optimizers. So the query optimizer is the part that takes your SQL query, which says what data you want to retrieve, and it figures out how to best retrieve it. In the past, this was always done by trying to calculate the minimum average cost. So if we're going to run this query a whole bunch of times on different data items, how is it going to be the cheapest on average? It turns out that's the wrong way to think about it if you want to bound the response time even in the worst case. So instead what Pickle did was it kind of switched the objective function for optimization to instead reason about the worst case cost and bounding the worst case number of operations that are going to be performed. One of the things that I figured out while doing this is that writing optimizers is very hard. And this is kind of a well-known problem. There was a lot of research done many years ago on kind of frameworks for building optimizers. And kind of the typical way people would do this is they would come up with languages, domain-specific languages for expressing rules. So you have some tree of relational operators, and I have some rule that's going to rearrange it in a way that I think it will run faster. So you're going to take some filter, you're going to push it down so it happens earlier, closer to the data source. So you have less data to process early on. So before, when people were coming up with these frameworks, a big part of the problem was developing the compiler that takes this domain-specific language and actually creates the code that will perform these transformations on these trees. Kind of the insight of this new project that I'm working on is that you can build this sort of a framework using the features of modern programming languages much easier. So in this particular instance, we're using this programming language called Scala, which is a hybrid object-oriented functional programming language. And what we found is that by taking advantage of language features like metaprogramming and algebraic data types and pattern matching, you can actually get a lot of the work, a lot of the infrastructure that's required to build an optimizer framework for free. And so what we're finding is that it's possible to express complicated algebraic rewrites of these logical plans in 10 lines of Scala, for example. And so I think what this is going to allow you to do is be a lot more agile in playing around with different ways of doing query optimization.